So welcome back, everyone. Today we're going to be talking about a topic that represents one of the more important uses of expectation maximization in biology context, and that's for learning a very particular kind of model called a hidden Markov model. Commonly abbreviated in HMM. So hidden Markov model is an extension of the Markov models we've seen earlier in the class. So you should all remember that a Markov model has three pieces to it, three components. It has a state set Q. We've got a Q1 up through, let's say, Qn. We've got a vector of initial probabilities, the initial probabilities of taking on any particular state, which we can call P1 through Pn. And we've got a matrix of transition probabilities, capital P, with elements P11 up through P1n, PM1 up through, PN1 up through PNN. And that defines the probability of transitioning from any one state to any other state in the model. So a hidden Markov model begins with these features, but then extends them with two additional components. First of all, it adds a set sigma, which we would refer to as the alphabet of the model, and sigma consists of some little sigma 1 up to little sigma m. This is known as the output alphabet, or simply the alphabet of the model. And we have another matrix B, which is known as the output probability matrix. And the output probabilities are encoded in this matrix B11 up through, let's say, B1m, and up through Bn1 through Bnm. And the way we would interpret this is that these are probabilities of outputting particular elements from the output alphabet when we're in particular states of the model. Because what a hidden Markov model does is take the standard Markov model but make the additional assumption that as we transition through the states of the model, we're producing outputs from the output alphabet. And then this additional probability matrix B is telling us which states from the output alphabet we're likely to emit as we pass through each state of the model. So, for example, we could take a model in which we have some Q, where maybe Q consists of states Q1, Q2, Q3. We'll make a probability transition matrix. And I'll maybe propose that the matrix looks something like the following. We've got 0, 0.5, 0.5, 0.5, 0, 0.5, 0.5, 0.5, 0. And this then would tell us that our model has a particular form where we've got three states, Q1, Q2, and Q3. And then from any state, we've got probability 0.5 of transition to either of the other states, with the implication that the self-transition probabilities are all 0 in this model. So that would be a basic Markov model. We would normally want to add in our vector little p. So we could make that arbitrarily. So maybe say we've got a 1/3 probability in each initial state. And then we would have a standard Markov model. And we could extend this to convert it into a hidden Markov model by throwing in some output alphabet. So maybe we'll say the output symbols are the letters A, B, or C, and an output probability matrix, which maybe will look something like the following. We'll say when you are in state 1, you output A with probability 1, 0 probability of B or C. When you're in state 2, we'll say that maybe you output A with probability 0.1, B with probability 0.8, C with probability 0.1. And when you're in state Q3, maybe you've got a 0.2 probability of outputting A, a 0.2 probability of outputting B, and a 0.6 probability of outputting C. So that would complete the specification of a hidden Markov model using this basic Markov model, which it then builds upon. And commonly, the way we're going to be using a hidden Markov model, the main use that we'll put them to, is that we will assume that all we get to see are the outputs, and very often what we're trying to do is figure out the states underlying those outputs. So in other words, it might be that if we simulate this model, we would get some sequence of states, just like with a standard Markov model. So maybe our state sequence is Q1, Q2, Q1, Q3, Q2, Q3, Q2, as we jump through the model according to the probability transition matrix. And we would say then that we get some vector of outputs, call this vector x, and each of these states would be emitting an output according to this probability transition matrix. So when we're in state Q1, this matrix is telling us that we always output an A, so we know there's going to be an A here and here. When we're in state 2, we usually output a B, so maybe there's a B here, but there's a chance that maybe we have something that isn't a B. Let's just say we get B's in both of the two states here. And when we're in state 3, usually we output a C, but there's an appreciable probability of an A or a B. So maybe it happens that we get a C here, but here we're going to get, I don't know, maybe a B by chance. And we'll also have a B here with high probability. And typically what we're going to want to do is assume that we don't actually get to see the states, we just get to see the outputs, and what we're trying to do is figure out the states. It's not the only use, we'll get to more of them later, but we might look at the sequence of states, look at the model, and at least superficially say that we can make a pretty good guess as to what the sequence of states was. So we know that usually when we're seeing an A, it's coming from state 1. There's a chance an A comes from state 2 or state 3, but usually state 1. So maybe we'll guess that we're in Q1 here and here. Usually when we see a B, it's coming from state 2. That can't come from state 1, but it has a possibility of coming from state 3. So maybe we'll assume these B's all correspond to Q2s. And usually when we see a C, it's going to be coming from state 3. It might have come from state 2, but more likely state 3. So we'll have this one C here, which we'll assume came from state 3. Now, if we do this in this superficial way I just described, we're actually going to make a mistake here. We're going to think we're in state 2 here when we know from a more careful examination of the model that it's actually impossible that we had 3 state 2s in a row because the self-transition probability is 0. But let's just say for the sake of argument that from this superficial examination we can do a decent job of guessing what states we were passing through based on the sequence of characters. Even in the simple case, we don't get it right completely though, and in more complicated cases, you really need to get into the theory behind these models to have a good chance of getting that sort of thing correct. So it may not be obvious why these are useful, but let me just give a few basic examples of where we see these in biology. So one of the most important applications of these, and one of the ones that really brought them to the attention of a lot of the biology field, is the issue of gene structure annotation. So gene structure annotation refers to the problem of, well, could correspond to several things, but typically we refer to this as identifying genes within a genome or identifying the intron-exon structure within genes. There are different levels of abstraction by which you can think about it. But let's say that we're trying to look at a eukaryotic genome and we're trying to figure out where are the genes and where are the introns and exons within those genes. We might propose that a hidden Markov model would be a way of doing that. And the way you would pose a problem like that is to try to create a hidden Markov model that produces outputs that look like gene sequences, and then try to figure out how a new sequence might have been threaded through that model. And that would give you an annotation as to how that might have been produced by the elements of a gene sequence. So to make that a bit more concrete, we might say that we have maybe some intergenic DNA, and I'll just call that state N. It's got some background output probabilities, so we'll assume our output alphabet then would be a sequence of let's say, nucleotides, A, C, G, or T, and we'll have some background frequency between genes. And every so often we leave that to start a gene. And we can superficially assume that maybe there's a preference for the 3 different positions, the 3 codon positions within an exon. So we'll call these states E1, E2, and E3. Those would correspond to the first, second, and third positions of each of the codons coding for an amino acid within an exon of a gene. And after one of these, we could return to start a new codon, or we could return to the intergenic region. So we would say that at that point we've finished the last codon in the gene, and maybe we leave. This could also correspond to UTR sequences, which I'm not getting into, so the pieces of the gene outside of the coding region, but let's say that could happen. Or we could move from an exon into an intron. So we might say that in an intron we have some preference for certain bases at the start of an intron, say intron star 1, intron star 2, to say that maybe there is a 2-base motif that tends to start an intron, and then maybe we've got some different frequency of amino acids, or excuse me, nucleotides within the intron, which you can represent by a state I, and then maybe we have some common ending motif for introns, we can represent by maybe a pair of states corresponding to the second to last and last base of the intron, and then at that point we jump back to the exon. This is a very simplified model of what an intron-exon structure might look like. There are cases that won't fit into this, but more or less this would describe how we can create a model that would encode a gene structure. And by putting the right frequencies of bases within these states and the right frequencies of continuing an exon versus moving an intron versus moving to an intron versus going back to an intergenic sequence, we can get something that generates or simulates sequences that look sort of like introns and exons. And as we'll see later in this class, once you've got that, you can then come back, take a new sequence, and try to figure out whether that sequence looks like it was produced by this model, and if so, which pieces of that sequence seem to be coming from this exon region, which from this intron region, which from intergenic, and so forth, and in that way, annotate the sequence, identify where the genes are likely to be and what the structures of those genes are likely to be. So that's an example of how we would typically use this, and later in the class I'm going to get to more of the details of the mathematics of how we would actually do that sort of application. Another common use of these is for recognizing different kinds of sequence motifs. We've heard a number of times, for example, about sequence motifs in the context of transcription factor binding. So we might have a motif finding HMM that recognizes some transcription factor binding site. And we might say that maybe there is a background state, just like in the Markov model we have here. Call that N. That would represent sequences outside the motif. And every so often it enters the motif. A transcription factor binding motif would typically have some short pattern or kind of consensus sequence it recognizes with some flexibility. And maybe we can say that there is a state M1 that represents the canonical first position. Maybe in that particular motif, usually it has an A in the first position, but a small fraction of the time it can have a C. We would encode that in the B matrix by saying probability of emitting an A here is 0.9, probability of emitting a C is a 0.1, for example. And we can have a state M2, a state M3, M4, and so forth. Markov model is kind of a heavy-duty way of coming up with something like this. It's more complicated than you typically need. There's simpler kinds of models, but it gives you a lot of flexibility these other model types don't commonly have. So, for example, if we have a motif like this, but we know that there is generally an arbitrarily length spacer between states 3 and state 4, we can throw in some spacer preference, a spacer state X, and say that we emit some arbitrary number of characters from X between M3 and M4. That would give us a way of recognizing a motif that can be split into two pieces that have this kind of window between them. It could also have probabilities of skipping over states if that happens from time to time. Basically just a more general kind of model for recognizing these kinds of sequences. And there are many other applications in biology, and of course, well, beyond biology, commonly associated, although not exclusively with applications in sequence analysis. So another would be a protein domain recognition. I'm not going to go into detail about an example here, but we could create hidden Markov models that represent patterns in amino acid sequences that tend to correspond to particular kinds of structural domains, and there are libraries of these kinds of protein domain hidden Markov models that people then use to recognize examples of these domains in newly sequenced amino acid sequences. So all of these are examples of why we would want this, but the reason I'm talking about this here is to go through this in part as an example of expectation maximization, in part just generally to go through how we would work with this kind of a model and how you would use this kind of model to solve the sorts of problems I'm describing here. So to get into that, we really need to talk about some of the computation that goes into working with hidden Markov models. So there's a very influential review article by Rabiner that is cited in the textbook. You can look that up if you want to read it. I would recommend that if you don't follow things after this lecture. And one of the things this review article did was break down the discussion of hidden Markov models into three basic problems, three computational problems we generally want to solve with an HMM. And when we get into talking about what you do with an HMM, I think it's worth discussing these three canonical problems, because it presents a good way of going through the algorithms, and unfortunately we do need to go through a few of these before we can actually get to the expectation maximization part, which comes into solving one of these problems. So one of the things we very commonly want to do with a hidden Markov model is, given some output vector, so given our outputs x, which we're assuming are things that we have been emitted from a simulation of the hidden Markov model, and given our hidden Markov model, which we would represent by this sequence, let's call it lambda, which would consist of our state set Q, initial vector P, our transition matrix capital P, our output matrix B, and our output alphabet sigma. So given that, what we want to do in problem 1 is find the best state sequence S. To produce X from lambda. So in other words, what we're trying to do is say, we have observed some sequence A, B, C, and so forth, like we have here. We're trying to find the best sequence Q1, Q2, Q1, so forth. So X then would be the outputs, S would be the sequence of states, and we're trying to infer that. So this is commonly the goal of creating one of these models. Very often that's what we're trying to do. So if we are creating a gene structure model, typically what we do once we have the model is we take new pieces of sequence, we're trying to find the sequence of states, and the sequence of states would then assign an annotation of gene structure to our to our nucleotide sequence X. So that's one of the things we'll commonly want to do. Another question we would often deal with is, given X and lambda, find the probability of X given lambda. And I'm not going to always write the arrows over these. So as I've done previously, sometimes I drop these arrows, but remember these are really vectors of multiple different values. But basically what I'm saying here is task 2 would be, given the outputs and given the model, find the likelihood of the outputs given the model. It might not be so obvious why we would want to do this, but you can actually think of that in terms of, let's say, this protein domain recognition problem. Let's say we've found an amino acid sequence, we've sequenced that, or we've discovered a protein and have done an amino acid sequencing of that protein. We want to know what it does. A common, simple way of doing that is to go to a library of known protein domains, and commonly this library would have some models of these domains, which might be HMMs. And then what we want to do is take that sequence and ask for each domain in our library, what is the probability of the sequence being output by domain model 1, that is our first HMM, what is the probability of it being output by domain model 2, what is the probability of it being output, what is the likelihood with respect to domain model 3, and typically we would also want to add in some notion of prior probabilities, so maybe we'd have a prior probability, so an expectation of how often domain 1 occurs in general, domain 2, and so forth. But basically, in doing this, we can come up with a likelihood of generating that sequence from each of our models, and then figure out, is it likely our sequence was generated from any of these models? If so, which one? How confident can we be in that? Or is it more likely? So that would be the second problem, or the second task we would commonly want to do with a hidden Markov model. The third thing, and this is where the EM is going to come in, is that very often we are given some X, or given our output sequence. Typically we would have multiple output sequences, but we'll just think of them as a concatenation of a single sequence, and we're given the structure of our HMM. By the structure I mean the discrete components of the model. So we're given Q and we're given sigma, and then what we want to do is find the quantitative components of the model, so the free or real valued variables corresponding to capital P, the vector little p, and capital D, so filling in the elements of these, such that we maximize probability of X given lambda. So in other words, finding the maximum likelihood model, where the model here we're assuming consists of the real value quantitative parameters, such that we maximize the likelihood of our observed data. You should recognize this as a kind of maximum likelihood model estimation, and know that that's a sort of problem for which expectation maximization is often useful. And indeed, in this case, the standard way of solving this with hidden Markov models is a kind of expectation maximization algorithm known as the Baum-Welch algorithm. Now, unfortunately, we have to get through some earlier theory and actually talk about how to solve these earlier problems before we can work up to the problem that's really our focus today, the Baum-Welch problem. So what I'm going to do is start jumping into how it is we would go about solving some of these earlier problems. And we can start with problem one. So to repeat, problem one is the problem of given an output sequence, so let's say our nucleotide sequences, and given a model, let's say our gene structure hidden Markov model, find the best sequence of states S to explain how our output sequence, our nucleotides, is threaded through the states of the hidden Markov model. So to put that more formally, what we'll say is that we are given our input vector, or excuse me, our output vector X, which will consist of, let's say, some X1 through X capital T. I'll say we have 1 through capital T steps in this model, or outputs. What we want is our state sequence S, which would consist of states S1 through ST, such that S is the thing that maximizes the argmax over S of the probability of X and S given lambda. That's the task we're trying to solve here. So to explain how we solve it, it helps to consider a bit what we could do with this if we knew what S was. So we're trying to find probability of X and S given lambda. And one of the first things we can do to figure out how we could solve this, given S, is to observe that with some basic conditional probability, the probability of X and S given lambda can be rewritten as the product of the probability of X given S and lambda times the probability of S given lambda. That's just basic conditional probability here. And if we knew S, then we could relatively easily figure out both of these things. So if we want to know the probability of X given S and lambda, that's saying we are assuming we know the sequence of states that the model is passing through as it's emitting the variables from X. We know lambda, so we know all the probabilities associated with that. And in terms of the way we've defined a hidden Markov model, we basically have all the pieces we would need to evaluate this. And pretty much all we need is this output matrix B. So in particular, all we would have to do is take the product over each step of our sequence, I equals 1 to capital T, of the probability B sub S sub I, X sub I, of outputting the character Xi from state Si. That's all we need to evaluate the probability of X given S and lambda. The other piece of this we wanted is the probability of S given lambda. And the probability of S given lambda we can figure out from these other pieces of the model. So our initial probability vector P and our transition probability matrix capital P. So our probability of outputting the state sequence S would be the probability our initial state is the first state of S, which would be little p of s sub 1. And then we would have to multiply that by the product over each of the transitions, so I equals 2 to t of the probability of transitioning from state s sub I to, state s sub I minus 1 to state s sub I. So that is the value p s sub I minus 1 comma s sub I. And this then would tell us the probability of the sequence of states being s, given that our model is lambda. And this would be exactly the same as if this weren't a hidden Markov model, just the probability of outputting a sequence of states from a Markov model, given the initial probability vector, little p, and the transition matrix capital P. All right, so what that's telling us is that this is easy to evaluate. If we knew s, we could easily figure out what the likelihood of the model is with respect to s. But as we should know by now, being able to evaluate an objective function is not the same thing as being able to optimize for it. And it's not quite trivial to see how we would optimize for s, so how we would find the s maximizing that likelihood, even though it's easy to see how we would evaluate the likelihood for a given s. And it turns out that this problem is solvable by a technique many of you should be familiar with called dynamic programming. So dynamic programming is a form of divide and conquer technique. Basically, it's a way of getting a solution to a complicated problem by building it up from solutions to successively harder subproblems. And generally, with a dynamic programming algorithm, we figure out how the algorithm should work and show it should work by showing that it's possible to evaluate the thing we're trying to find in terms of some kind of recurrence relation, a way that tells you how to solve a version of the problem using solutions to slightly easier versions of the problems. In particular, there is a dynamic programming algorithm called the Viterbi algorithm that is going to solve that for this particular task 1 with our hidden Markov models. So with the Viterbi algorithm, what we're going to define is a particular quantity that I'll call m sub ij, which will describe the substructure of the model. In particular, m sub ij is going to tell us likelihood for, informally, the best s up to output j, so up to the jth step in the model, given the sequence ends in state qi. So in other words, we're defining m sub ij to be the best possible sequence s1, s2, s3, and so forth up through sj, given our input sequence x, such that s sub j is state qi. So that's what we're going to define here. And what we'll show is that if we can solve this for small values of j, we can use that to easily solve for larger values of j. And in particular, we can observe that this will follow the following recurrence relation. Mij is going to be given by, well, we'll start here with just the definition. Mij is the sequence s1 through sj, maximum over that, of the probability x1 through xj and s1 through sj, given our model lambda, and given sj is qi. That's our definition here. And we can break this down to get a way of solving this in terms of solutions to slightly easier subproblems by saying that this is the maximum over all possible values k of the probability of states x1 through xj, given lambda, and given sj is equal to qi, and sj minus 1 is equal to qk, times the probability of the state sequence s1 through sj, given, lambda. So in other words, what I'm saying here is that if we have the solution to the maximum or the maximum likelihood set sequence of states S1 to Sj, that has to be the same as the solution to the maximum likelihood sequence S1 through Sj minus 1, ending in Qk, then jumping to Qi, maximized over all possible values of k. So there has to be some second to last state value in this sequence. We're just maximizing this quantity over all possible choices of that second to last value. And we can use that to do a little simplification here. So we can say that that is equal to the maximum over k, again, of the probability x1 through xj minus 1, given lambda, and given that s of j minus 1 is qk. So that's saying the probability that we get the first j minus 1 elements of our output given our model, and given the first j minus 1 elements of our state sequence, assuming it ends in state k, times the probability that we've got S1 through Sj minus 1 given lambda, so the probability we output those j minus 1 elements of our sequence, times the probability Sj is Qi, given Sj minus 1 is Qk, times the probability of outputting Xj, given that Sj is Qi. So this is putting together all the pieces and basically saying that if we pick our previous state before state j, so state j minus 1 to be Qk, maximize that over all possible choices of k, then we have to get the maximum for the overall sequence, which is simply the thing we're trying to find here. So at that point, what we can say is that we've reduced this into basically two pieces here. So we've got this thing, which is maximizing over k, more or less the thing we're trying to find on the first j minus 1 states, and this thing that's telling us the probability of getting now the jth state to be Qi, given the maximum choice over those k minus 1 states. And we can rewrite that as follows, recognizing that that's simply the maximum over k of this quantity we're trying to define here on the first j minus 1 steps. So in other words, the maximum over k of m sub k j minus 1, then multiplied by these pieces here. And these pieces are things that are easy to evaluate in terms of the model. So we need to know, for example, the probability that the state at step j is Qi, given the state at step j minus 1 is Qk. That's directly given by our transition matrix. So that's going to be p sub ki. And we need to know the probability that if the final state is Sj, that we output the observed value Xj from that model. And that is going to be b sub I Xj. And this is basically what we need to establish a dynamic programming algorithm. We've shown that we can compute the value m sub ij by maximizing over possible values k of m sub k j minus 1. So if we know the value of m for every second subscript here up through j minus 1, then we can figure out what it is for every value j. Now there's one small catch here, which is that we can only figure out what the values of these are. We can only figure it out for a value j if we know the value for j minus 1. So we don't quite have what we need because we don't know a way of doing this if j is 1, because then there is no j minus 1. So commonly in these cases, you'll need a base case. You need some way to start a dynamic programming algorithm. In particular, we need to know the value of m sub I for any I at position 1, but that we can figure out pretty easily as well. That is simply the probability that we output character 1, x1, given that state 1 is Qi, and given lambda. That's simply the definition of the thing we're trying to optimize here. We can say by conditional probability, that's the probability of outputting the output 1, given that state 1 is Qi, and given lambda, times the probability that state 1 is Qi, given lambda. and that is simply the output probability, b sub I x1, and the initial probability, p sub I. So that then gives us our base case. And putting these things together, this base case and the recurrence relation gives us everything we need to be able to figure out the complete set of probabilities m sub ij. And if we solve that for every value of j and every value of I, as we'll see, it will give us a solution to our original problem, which is to find the maximum likelihood state sequence. So a dynamic programming algorithm is commonly represented as filling in a table or filling in an array, where in this case, the elements of the array in one dimension are going to be the steps that we take passing through the model. So we'll have steps 1, 2, 3, 4, and so forth up through capital T, we said. And the rows of this array or matrix are going to be the states of the model. So we'll have state Q1, Q2, and so forth up through Qn. And we can use the pieces we have here to figure out the value of every element of this array, where each element is going to be one of our Mij values. So we know from our base case here how to figure out Mi1. We can figure that out directly from our output matrix B and our initial probability vector P. So we can just run through here, assign each of these directly. And then we can use our recurrence relation here to figure out the value of each of these elements in row 2 or column 2, given there were elements in column 1. So we could look at, for example, element 1, 2, M12, which is going to be the probability that we output the first 2 steps of the model, or given that we end in state 1. And we can figure that out by saying that the maximum likelihood of ending in state 1 after 2 steps of the model is going to be the maximum over all possible states we could have been in on the prior step of the likelihood of outputting the first step and ending in that state k times the probability of transitioning to state 1 in step 2 and then outputting the next value from state 1. And we can do the same thing to assign a value here and here and here and so forth. So basically, we can just start going through all of the columns of the matrix, filling them in until we get to the last row of the matrix. And then at that point, we have our values, m sub ij. We will also want to keep track at each of these steps of which value of k gave us the maximum. So maybe for step 2, the maximum k came from for state 1 in step 2, maybe the maximum k came from state 2 in step 1. For state 2, maybe it came from state 4, and so forth. Just keep track of that. And then when we get to the last row, what we really want to know is what I'll refer to as m star, which is simply the maximum over all the possible values mi capital T. So in other words, by the final row, what we're computing is the maximum likelihood value of a state sequence terminating in step I for each state I for each possible state I. We just maximize that over states I, and then we get the maximum likelihood value for the best possible assignment of states, sequences of states S through the whole set of values, and we can use that memory of which of the things was the maximum at each step to do what's called backtracking, to figure out what sequence of states we used to get those maximum values as we pass through the model. So at the end of this, we go through what's called the finalization or finalized step of this. We get the maximum likelihood value for the whole model, m star, and we can use backtracking to go back and figure out what actual sequence of states would have given that maximum likelihood assignment. So that basically is the Viterbi algorithm. All right, so that solves our problem 1. And that basic structure is going to give us most of what we need actually to solve problem 2. So problem 2 is asking a different question, but it's a question that is very similar to the question we're asking in problem 1, or at least depends on very similar kind of intuition to solve it. And to summarize, basically what step 2 was is asking us to evaluate. So in other words, we're saying over all possible state sequences X, all the possible state sequences S, all the possible sequences of states, how likely are we to produce the output sequence X, given that our model is lambda? Well, we can consider how that would be done if we imagine that we could simply sum over all of the possible S's. So in other words, probability of X given lambda would simply be the sum over possible values S, so possible sequences of states S, of the probability of X and S given lambda. So I'm just saying, for every possible S, we would be evaluating the probability of X and that S given lambda, summing over every possible S. And by our rules of conditional probability, just like before, we can break that apart into the probability of X given S and lambda times the probability of S given lambda. And these are things we know how to evaluate. Given an S, we can evaluate the probability of X given S and lambda. It's going to look like the following. So that's sum over S, and this first term would turn into simply what is the probability of outputting all of the individual observations in X, given that our state sequence is some known S. That comes directly from our output matrix. So we've got B of S1, X1 times B of S2, X2 times B of S2, 3S, X3, and so forth, up through B of S of capital T, X of capital T, and that then is going to be the probability of the outputs given our state sequence S. And likewise, we can figure out the probability of the state sequence S given lambda. It's simply the probability we start in state S1, that's piece of S1 from our vector little p, times the probability we transition from S1 to S2, which is piece of S1, S2 from our transition matrix, capital P, times the probability we transition from S2 to S3, etc., up through the probability we transition from ST minus 1 to ST. So that then tells us the likelihood of outputting X given lambda. There's a catch here, though, and that is that this is not generally something we're going to want to evaluate. In principle, if we had enough time and enough compute power, we could run through this, but it's generally going to take a lot of time and a lot of compute power. And the reason is that there's simply too many possible choices of S. If we've got n states in our model, and we've got capital T steps that the model is going through, that we're trying to explain, for which we're trying to explain the likelihood, then the number of possible state sequences is n to the t. For many of these sequence analysis problems, n might be, if you're talking about a motif problem, n might be on the order of 5, t might be on, you might be going through a gene sequence on the order of 1,000. 5 to the 1,000 is a pretty big number, and that's on the small end of what we might be dealing with. So this is not practical. We can't actually do it this way, but it does give us some intuition of how we are really going to solve it. And in particular, what we're going to do is solve this problem by using something very similar to the Viterbi algorithm to construct this S iteratively, or that is to sum over the S in pieces. So use solutions to this problem for partial bits of S and see how we can extend a bit further. So solve this for, let's say, the first j characters, and then use the solution to that to easily get the solution for character j plus 1. And this is solved by another dynamic programming algorithm. It's very similar to the Viterbi algorithm, known as the forward algorithm. So the forward algorithm computes a quantity alpha sub ij, which is exactly what I just described, a partial solution to this problem of finding the partial state sequences x1 through xj, so solving this for the first j steps. That is, probability, our sequence starts with x1 through xj, and simultaneously that we have a partial state sequence that terminates with state j being q sub I, given our model. So in other words, it's the partial solution to the problem. So alpha ij is the solution for the first j outputs of the model such that the final state after those outputs is I, and then it'll be summing over all of the other states up to that final state j, which we're declaring to be I. And if we can solve this, as we'll see in a moment, we can use that to get the next further step. In particular, we would have a base case, as with our Viterbi algorithm. So we need to figure out how this starts and show that we are able to solve this for the smallest possible value of j. That is, that we can find alpha I1. Alpha I1, by our definition here, is equal to the probability of x1 and s1 being qi, given lambda. And we can figure out this probability by taking our conditional probability rules. It's the same as the probability of x1, given that s1 is qi and given lambda, times the probability that s1 is qi given lambda. The probability that we output x1 given that s1 is qi and given lambda is simply our output probability b sub I comma x1. And the probability that our first state is qi is simply the value p sub I from our initial probability vector little p. So we've got a base case. We can fill in all the values of alpha for j equals 1. We then do our basic iteration here, and we want to figure out what alpha ij is for j greater than 1. And we can do something very similar to the Viterbi algorithm, except that effectively what we're doing is summing over possible values of s rather than trying to find the maximum value of s. So if we want to get to the next step of this, that's simply equivalent to saying that we're going to sum over all possible states k equals 1 to n of the probability of terminating in state k at step j minus 1 times the probability that we then move from state k to state I, that's p sub ki from our transition matrix, capital P, and then output from state I character xj. So this then is going to be the basic iteration of our model. To get alpha ij, we can figure that out from alpha kj minus 1 by summing over all k of alpha kj minus 1, which is the best possible probability, or it's the likelihood of being in state k at step j minus 1, given the first j minus 1 elements of our sequence, times the probability of then transitioning from state k to state I, times the probability of then outputting the jth observed value from state I. So that then is our basic iteration. And then at the end of that, we're going to have some kind of termination step. And just as we are switching in the Viterbi algorithm from maximizing to the forward algorithm summing here, we do the same thing in our termination or finalization step. We say that finally the probability of outputting x given lambda is going to be simply the sum over all possible values of the last state, so I equals 1 to n, of alpha it. So the final set of alphas, alpha I capital T, is going to be the probability of outputting our complete set of observed variables and ending in state I. You sum that over possible values of state I, you get the complete likelihood of outputting the sequence given the model. And this is something we can solve very similarly to how we would solve the Viterbi algorithm. So we can create a very analogous table of values where we've got our states in the rows here, Q1, Q2, Q3, Qn. We've got the steps in the model, 1, 2, 3, up to capital T. And then we apply our base case to get the values of alpha from step 1. We just need to know our B matrix and our P vector to do that. And then once we've got those for each of these new values, we're just summing over values from the previous column. So if we want to know the value of alpha 1, 2, that would go here, what we would do is say sum over all of the possible values of alpha I1, the probability of ending in state I, times, or I guess I've been calling that k, but let's say sum over alpha k1, probability of ending in state k, then transitioning to state 1 here, and then outputting the proper character for step 2 in state 1. So we sum there, we can get that value. Likewise here, we sum over all of these, get this value, and we can just run through one column at a time, each time using the prior column to generate the next one with a small amount of additional work. And then in a polynomial amount of time, we get to our final answer, probability of x given lambda, that is the likelihood of the model given lambda. So that then is the forward algorithm. So the forward algorithm gives us a solution to our problem 2. And this actually gives us part of what we're going to need to solve problem 3. Before we get to problem 3, I want to talk about one alternative way we can solve problem 2, and that is with a slightly different algorithm related to the forward algorithm known as the backward algorithm. And the backward algorithm does more or less the same thing as the forward algorithm, except it does it from the end of the sequence moving towards the beginning. And we're going to need this when we get to the EM part, which we're gradually working our way towards. So the backward algorithm solves the problem of finding a beta ij, which is sort of like alpha ij, except whereas alpha ij is talking about the likelihood of a prefix of our full set of outputs, beta ij is going to be talking about the likelihood of the suffix, of the ending of the sequence. In particular, we're going to define beta ij as the probability of outputting states xj plus 1, xj plus 2, etc. up through xt, given and ending in sj being qi, given lambda. And what we're going to do is show that this can be done very similarly to the way we solve the forward algorithm as a more or less an analogous dynamic programming algorithm. We can initialize, and initializing just means figuring out for every possible state I, the value beta it, so figuring out the betas in the last row. The way we've defined this has to do with the outputs of all the characters after I, which I think I probably should put the conditional here to make this strictly correct. So, sorry, this is the probability of outputting the suffix, given that we're in state I at step j, and given that we are in model lambda. What we would end up with is that beta it is going to be simply 1. If you're at the final step of the model, there is no suffix after it, so your probability of outputting nothing and following the model is 1. And then we can iterate backwards from there, moving left by saying beta ij is equal to sum over k equals 1 to n. So the sum over all of the steps of the model, in this case, following the one that we're now trying to figure out here, of the probability of transitioning from state I to state k, that's p sub ik, times the probability of outputting from state k the symbol xj, so the thing we see in step j of our output sequence, times the probability of then producing the rest of the sequence, which we've defined to be beta sub k, j plus 1. And that's going to give us the value of beta sub ij for any value of I, and for j, given that we've already figured out beta for j plus 1 for all the values of k. So in other words, that's going to give us a way of filling in a matrix that is more or less the reverse of what we were doing with the Viterbi and the forward-backward algorithm. We've got a very simple base case. We just put 1s in the final column everywhere, and then we can use this formula to figure out all of the values in the second to last column, use the second to last column to figure out the third to last, and so on, going backwards until we get back to the first column of the matrix. And then we can finalize very much like we did in the forward algorithm. We could just sum over possible values in the first column of the matrix and get an alternative solution to our problem of setting the likelihood of the model. Now you might wonder why we would bother having a backward algorithm if we already have the forward algorithm solving the problem. One of the reasons is this actually gives us another interesting way of solving the first of our 3 hidden Markov model problems. In particular, it lets us define a quantity gamma sub ij, where gamma sub ij we're going to define to be the probability that state j is qi, given the full sequence of outputs x1 through xt, and given the model. And we can figure out what gamma sub ij is in terms of the outputs of the forward and the backward algorithm. So in terms of the beta and the alpha values, it's simply alpha ij, beta ij. So that is the probability of generating the prefix of the first j characters and ending in state I, times the probability of generating the suffix of all the characters after j, starting in state I, and then normalized by the total probability of outputting x given lambda. And we can figure out this total probability by simply saying that that's going to be this quantity alpha ij, beta ij, summed over every possible value of I. So in other words, gamma ij, the probability of being in state j or state I at step j is simply alpha ij, beta ij divided by the sum over I prime of alpha I prime j, beta I prime j. So this gives us an alternative way of saying what the best state sequence is. It's not quite the same as we would get from the Viterbi algorithm. This is saying for each individual state, what is the probability of being in that state at each step in the model. You could just pick the maximum of these and get a best sequence of states in one sense, sort of more or less the expected sequence of states. That's not quite the same as the one complete best sequence of states, which is what Viterbi gives us, but does give us an alternative way of solving that. And it also is going to give us a way of solving the third problem that we're getting to. So it's going to turn out that we need these alpha ij values. So because of that, people often refer to the forward and backward algorithms together as simply the forward-backward algorithm. Because even though you don't need both of these to solve the problem 2, usually you're actually trying to find these gammas, which we are going to need to solve problem 3. But basically that gives us the forward algorithm and the backward algorithm, and that gives us a way of computing these gamma ij values, which, as we'll see shortly, is something we're going to want to do. And that really finally is bringing us to the thing we're going to want to solve with expectation maximization, which, as I said, was really the motivation of doing this in the first place. All right, so coming back then to our problem 3. Problem 3 for dealing with HMMs is, given x, find lambda, maximizing probability of x given lambda. So it's a simple model maximum likelihood problem. We're trying to find the model maximizing the likelihood of our data. And to understand how we would do this, it helps to think about how we would do this if we also knew s. So if we just amended this problem to say, we know x and we also know the state sequence s, and we want to know the maximum likelihood estimate lambda to maximize the probability of x and s given lambda, that would actually be a very easy problem to solve. So normally the way we would think of this is that we've got some training sequences. So maybe we've got the sequence x1, x2, x3, x4, and so forth. We would normally assume that we've got more than one of these. Maybe we've got x1 hat, x2 hat, x3 hat, and so forth, x1 double hat, x2 double hat, so a set of different training sequences. If we imagine that someone has actually gone through and told us what the state labels are, then it's pretty easy to solve this model problem. Maybe we've got S1, S2, S3 is the sequence of states for this example, S1 hat, S2 hat, S3 hat, sequence of states for this one. What we're trying to do in this problem is figure out our initial probability vector, little p, our transition matrix p's. If we want to know our initial probability vector, little p, what we could do is look at all of our example sequences, see how often the first step of each example sequence was labeled with each possible state, so S1, S1 hat, S1 double hat, and so forth. And the fraction of each of the states in those initial positions would tell us p. So if 1/3 of the time we're in state 1 at the first step of a labeled training sequence, then we know that p sub 1 is 1/3, and so forth. Likewise, we could easily figure out what the values of our transition matrix P should be, at least get our maximum likelihood estimates. If we want to know the probability of transitioning from state 1 to state 2, we just look for all of the times we're in state 1 as we run through these labeled sequences and ask what fraction of those are then followed by state 2. That would tell us the element P sub 1, 2, and we could do the same thing to find every element of capital P. And likewise, we could find our elements at B. If you want to know the probability that state 1 outputs symbol 1, what you do is look at all of your training sequences, see how often you see things labeled with state 1, and you ask what fraction of them are labeling something that has an output of symbol 1. That gives you the probability for that element of our output matrix B, and we could repeat that for every element of B. So if we knew S, if we have labeled sequences, it's very trivial to figure out the quantitative parameters of our model. But where the problem gets hard then is that we're assuming here that we don't have labeled data. We just have an output sequence or multiple output sequences, and we're trying to figure out from those what the maximum likelihood model assignment is without knowing what the state sequence is. So that should give us a hint, though, about how we can solve this. In particular, I've already told you that this is a problem we can solve by expectation maximization. There is in particular an EM algorithm known as the Bound-Welch algorithm, which will solve this problem. And we should note that if we have an EM problem, or we have an EM solution, that is, we have an EM algorithm to solve for this, then that algorithm is going to be largely dictated to us by the choice of latent variables. So if we know the latent variables, then we can figure out the E and M steps that relate to those latent variables. And by telling you that this problem is easy to solve if we know the state sequence, you should be able to guess more or less what the latent variables are. In particular, our latent variables should be something that makes the problem easy to solve. If the state sequence makes the problem easy to solve, then let's say that the state sequence is our set of latent variables. What we'll do is not quite what we've done with our previous examples of EM. This one's a little trickier because we're not going to be able to get away with the simplifications we used in our earlier examples of just using the expected values of the latent sequence. But we also don't have to quite go to a complete probability distribution of the model. And that's part of why I like to use this as an example of EM. It's a little harder, but we can see some of the tricks that come in to a harder case. In particular, what we're going to want to do is find the probability distribution or a state sequence specified in terms of a set of what are known as sufficient statistics. And sufficient statistics basically means a set of quantities we can compute which are enough to give us the probability distribution over possible state assignments. Once we've got the probability distribution over state assignments, that will be our set of latent variables y. So more correctly, y would be the state assignments. We get the probability distribution over y. Then we should be able to do our E step, which is estimating that probability distribution, and our M step, which is finding the maximum likelihood model with respect to that probability distribution over state assignments. So it will turn out there are two kinds of sufficient statistics we're going to need here. The first of these is a quantity they'll refer to as C sub t, this is a little t here, I comma j. And C sub t, I comma j, is going to be defined as the probability we move from state I to state j, qi to qj, on step little t. And the other sufficient statistic we're going to need is gamma sub I little t. And this is the gamma we already figured out here. Simply the probability the model is in state I on step t of passing through our input sequences. And if we can figure out these are going to give us everything we need to get at least what we need about the probability distribution over state assignments to solve our M-step. So in particular, let's suppose we have those quantities. So we're assuming here that we know the probability on each step of our sequences or each step of our training data that we're moving from any given state Qi to any given state Qj, and we know the probability that we're in state I at any given step of our sequences. Then we can solve the M step as follows. So in the M step, just like in the labeled example, what we're trying to do is estimate our model. We're trying to maximize the likelihood of our model, and that consists of little p, big P, and capital P. So if we want to get a maximum likelihood estimate of the elements of little p, we can take some p sub I. P sub I is the probability that we are in some state I at the start of a training sequence. This is simply given by gamma sub I1. So in other words, the probability that we start our model in state I is the same thing as the probability that our state at step 1 is I, which is the definition of gamma I1. So if we have gamma, we can figure out the maximum likelihood estimates of the elements of little p. We want to figure out big P. That means we want to know each element P sub ij of big P, and that we can figure out using our C sub t ij vectors. We're trying to figure out the probability you transition from state I to state j, and that is simply given by, or at least estimated by, the sum over all possible steps of the model. Let's call that little t equals 1 to big T minus 1. Making it minus 1 because we need to observe a transition of C sub little t I, j. So in other words, summing over every step of our input sequences, what is the probability we made the transition from I to j on that particular step, and then we just need to normalize that. This is effectively asking the probability our next state is j, given the prior state is I, so we need to normalize by the probability the prior state is I, and that's simply sum over little t equals 1 to capital T minus 1 of gamma I little t. So the probability we're in state I at step t. And then the overall ratio here is the probability that we move from state I to state j in step t divided by the probability we're in state I at step t, which is the probability we move to state j given that we were in state I at step t, or summed over all t. So that gives us the next piece of our maximum likelihood model estimate. And the last thing we need is our output probability matrix capital B, and that consists of elements E sub jk, and we can estimate those by asking what is the probability that we output any given character k from our alphabet, given that we're in state j, and we can say that that would be given by summing over all possible steps of our model, t equals 1 to capital T, conditional on that state being a state that outputs simple k. So in other words, conditional on x sub t being sigma sub k, or output simple k, of the probability that we are in state j at that step t. So this is then the sum over all probabilities of states in which we output k of the probability of being in state j at that step. And then this is also a conditional probability. It's the conditional probability of outputting k given that we're in state j. So to get the right conditional probability, here we've got the probability of outputting state outputting symbol k and being in state j, we need to normalize by the probability of being in state j, which is simply the sum little t equals 1 to capital T of gammas of jt. So what this is showing is if we have the c's and we have the gammas, then we can get maximum likelihood estimates of the quantitative parameters of our model, and that is an m step. All right, so we can figure out our m step, but it's worth noting here that this is not something that's linear in our latent variables. We would not be able to compute out these probabilities given just the expected values of our latent variables, that is our expected state assignment. You wouldn't be able to do these normalizations where you're dividing. And so that's where we need to use these sufficient statistics. We need something that gets us close to actually having a full probability distribution over possible model assignments, and that then brings us to the E step of our model. And the E step is simply figuring out the sufficient statistics, of figuring out the C's and the gammas. We already know how to get the gammas, so the gammas are simply the outputs of the forward and backward algorithm. So basically, we get our gamma ij's by running forward-backward. So we run forward and backward. That gives us the alpha ij's and the beta ij's. We use those to get the gamma ij's. And forward-backward algorithms are also going to give us most of what we need to get the c's, which is the only other thing we need to complete our E step. So you get some c sub t of ij. What we're going to see is that we can figure that out as well, given these alpha ij's, beta ij's, and the other components of our model. So in particular, we can define c sub t ij, which again, remember, is the probability at step t of passing through our sequences that we're making a transition from state I to state j. And we can define that as the probability alpha sub I comma t of outputting the prefix of all of our sequences, so all of the values up to state t, such that we end in state I, so that we're ending in this I here, times the probability we transition from I to j, that's p sub ij, which we've estimated in our m step, times the probability of outputting the suffix of our observed values, that's going to be beta sub jt, so the probability of outputting the rest of the observed sequences, given that we're in state j after this jump from I to j, times then the probability of outputting that one additional value we saw during this jump, so b sub j x t sub 1. So in other words, the probability that we output character x sub t plus 1, so the t plus first character in our sequence, given that we've ended in state j after this jump. And then we just need to normalize, so this is giving us the probability that we make this particular jump on state j. We just need to normalize by all of the possible values, I prime and j prime, by which we could be making this jump of alpha I prime t, p I prime j prime, beta j prime t times beta j prime x sub t plus 1. And that's going to give us then our c sub t ij values. And that pretty much is the Baum-Welch algorithm. So we've got an m step, we've got an E step, we can start our model, we make some initial guesses, you can then run an E step, get your gammas and your C's using the forward and backward algorithm, some additional computation. Once we've got the gammas and C's, we've got everything we need to improve our estimates of little p, capital P, and capital B, and then we just go back and forth, and like any EM algorithm, this will hopefully converge on a good fit of your model to your data. So in practice, things can get quite a bit more complicated. Ideally, what you would hope you have is at least some labeled training data. So it might be that maybe you're creating a gene finder and you have some labeled genes, but also lots of sequence that probably has genes but isn't labeled. There are always ways you can work around that by throwing in additional prior probabilities on top of the model, or using the data you know to kind of get things started, to get good initial estimates, and then train on the rest of the data. And there are also complications that come up in practice where sometimes you don't quite want your standard hidden Markov model. Maybe you want to change the probability distributions a bit. Maybe you want to give it some extra help to find the right answers. You don't get stuck in a local optimum or spin off away from the correct values, so diverge from the values you're trying to find. There are a lot of details that come into the practice here, but that's the basic idea. I would recommend, for those who really want to know how to work with these kinds of models, you go to some more advanced material on them. I think a very informative paper to look at if you want to know about how these are used in biology is the GenScan paper, which I cite in the textbook. So GenScan was the first really successful eukaryotic gene finder. It used a kind of extended hidden Markov model and goes into a great deal of detail about how you design a hidden Markov model to find eukaryotic genetic sequences, as well as ways you need to break from the basic HMM to deal with some complexities like, for example, the fact that introns and exons don't have the right distributions of lengths to strictly behave as an HMM or a Markov model in general should behave. But basically, I hope this illustrates an important class of models in biology, as well as showing at least one example of how working with EM can be a bit more complicated than the simple examples we'd seen in the previous lecture.